Good afternoon, everyone. First of all, I would like to express my sincere gratitude to my supervisor, Professor Kamata. Thank you for his encouragement, patience, and valuable guidance so I can finish this thesis. And thank you very much for Professor Lepage and Professor Felicity for attending my thesis. So my name is, first of all, I want to introduce myself. My name is Dida Kharisma Akbar. I'm one of the lab members of Kamata. So today I would like to start to briefly explain the outline of my today's presentation. So we briefly introduce regarding the research background in this research field, and then the related works that it might be related with our works, and then the problem statement which is the current existing method may face, and then the proposed association method in order to solve the problem statement that we have been stated in the previous section. We solve it by using first of all the person detection to detect the person. After the detection, we do the tracking. So, and we will show some experiment result on the video data set and end it with conclusion and future work. First of all, the background, why we do this kind of research. The rapid advances of visual sensors lead to the decreasing cost of cameras. So it makes sense, people nowadays tend to deploy multiple camera setup rather than single camera. And then this kind of multi-camera setup enable new system that use cooperatively multiple camera to solve such as occlusion problem, which is very common in single camera tracking. So in this figure below, we can show some example of a typical overlapped multi-camera approach using 4 cameras. The next part is the motivation, why we need to use multi-camera based approach, why not on single camera. So the first one is makes sense, is extend the surveillance area by observing from different point of view. And then the second thing is the first main, our motivation, which is to solve the occlusion problem by using several cameras simultaneously. As you can see in the red circle, there is an occlusion. We cannot see that actually there are 2 persons, but only appear 1 person here. And another view in the camera 2, we got a clear view that there are actually 2 persons there. So the related works here, there are at least 6 related works, but we want to make some stress point that we make a very, very careful consideration related works from the EPFL from Switzerland, which is the number 1, number 2, number 5, and number 6. Because we use we implement the same person detection, which is based on POM. We propose it based on using the background subtraction and ground discretization in order to detect the person in the ground plane. And then the main difference in all of those methods and their method is only actually in the person tracking, which is the recent method they use MCNF, and then the earlier years they used another method for tracking, and then earlier using another method again, dynamic programming. So we can conclude that actually the person detection they use is the same. Basically, it's based on POM, and we use also the base POM, but by our own implementation, background subtraction and ground discretization. And also in the person tracking, we do our own implementation in using the global nearest neighbor association to enable the frame-by-frame tracking approach. So we would like to explain a bit regarding the POM. What's the concept of POM? So the concept of POM, as we could see here, is a ground plane, a rectangle ground plane that could be seen from all camera views. So at first, these rectangles, we model an individual as a point at a location x, y, y, y on the ground plane. And then for each k, we discretize from number 1 until g. So for example, this one xk1, and then xk16 you could see, and xk148, and until the end, xk equal to g. So for this one, we need to at first discretize this ground plane into a finite number of grids as stated like this. And then the next part, for every k, we approximate the probability of the occupancy in specific grid location k given the binary images from all cameras. So we got the binary images from B1T until B3T. For example, we have 3 cameras here, but it could be extended for as many as we want. So from the first time frame until the T time frame, which is the end of the video time sequence. The next part is we want to talk about the CMT. This is the main algorithm that we use to track the person. So given a sequence of images I1 until IN, and initialization region B1. B1 is indicated as the bounding box inside the I1, and then the object, the object in this case is modeled as a set of key points inside the bounding box B1. We already initialized at the first time. So given that each key point here, there is a location R inside the template coordinates, which is inside the bounding box, and then the binary descriptors is only 0 or 1. And then each key point is very important here to cast a single vote for the center of object interest. Why they need to cast a single vote? It's in order to decide whether this object is visible or not. This is what the tracking means for. They need to specify whether the object is visible or not, so they need to cast for the center of the object interest, and then to find the consensus between them to remove these outliers. This one, the key point, vote for the center, key point, this is the result of the consensus. So this is example that this is the bounding box, and then there are 5 key points here and vote for the single. And then wherever the object even rotate, they can still detect this object because they still vote the same center. So we move to the problem statement. The first one is the problem in the time consuming here, because the previous existing work is using batches of frames, require 100 or even 1,000 iteration procedures to achieve probability mode. Though the result is very good, but they cannot produce the tracking result in real-time processing. Means that it cannot produce the tracking result frame by frame. That's the main thing. And then the problem next is occlusion, which is also still exists, also even though we use multi-camera approach, that let's say there are 5 and 8 here, because it's passing by each other, the identity 5 and 8 is switch. And also if we visualize in the ground plane here, the trajectory yellow means there is this big possibility that there is this identity switch happens here. So the main concept of our proposed association method is we want to do the tracking frame by frame approach. So how to do that? In each frame, we associate the detection of POM and the predicted tracking of CMT. So at first we need to detect first by POM, and then next generate the tracking result of CMT and do association here to, generate the final result, which is the final tracking result. So in the person detection, we detect first the person, here the input image frame from different camera views. We do background subtraction here to get the binary images, and then the ground plane discretization to get the corresponding ground plane for each camera views. So to do the background subtraction, we choose to use the fuzzy adaptive SOM, and then the ground discretization is processed based on the DLT algorithm, discrete linear transform, which is proposed in this reference. In detail, why we choose POM is based on these 3 reasons, actually. So the advantages of POM is relatively faster computing time compared to existing method. It makes sense because the input is only binary images. It's really, really fast. And then the next one is only requires simple homography. They doesn't need to full camera calibrations. In this case, only this ground plane discretization to find the correspondence between camera views. And then the last thing is one we want to exploit. This is the geometrical mapping of the result of bounding box of POM. We will, exploit this geometrical relationship of the bounding box to generate an efficiency tracking result. So we did several experiments to choose the best of background subtraction, because it's very well known method, but a lot of background subtraction out there. But we did several comparison here, as we can see. The 4th one is the one that we choose, which is fuzzy adaptive SOM background. And then the second one is mixture Gaussian and adaptive median. As we could see, the 4th, or the one that we choose, is mostly, the 3rd and 4th is almost the same, but we can see that the 4th one is more fill up the gap between the blobs, binary blobs. So we choose this 4th one as our background subtraction. And then the ground discretization, like I said, we use the DLT. Let's say we got the homography matrix for each camera view. We use the DLT and further derives to get these equations. So this one is from one image view, one coordinate view to another coordinate view. So from the top view of the ground plane, we could move, we could find a correspondence in each different camera views, just using the homography matrix for each camera. So the sample result, this is actually a number from 1 until G number. So there will be correspondence. Let's say this is number 1 here, but the number 1 in this different camera views will be here, or this one also will be here. So the main idea of the ground discretization is to find the correspondence between different camera views. So we move to the proposed person tracking. How we do the person tracking? We propose using the center ground points of the bounding box of POM and CMT to do this, and then perform the association based on global nearest neighbor. And in order to handle the occlusion when we do the tracking, we introduce the camera view switching mechanism, and it is based on the estimation of occlusion in every camera view. What's the difference? We exploit the geometrical mapping of bounding box from POM, utilize the tracking in only one camera view. This is done because we can get the relationship between different camera views. So we only need to track in one camera view and distribute the result to the other camera view like this. Why we choose CMT? Because it's fast. It's based on the fast key point detector, like SIFT or BRIS. We can choose anyone, and then low computational time of binary descriptor that they use. So the first thing, suppose that we have n bounding box of POM detection and a person tracker CMT bounding box, person tracker CMT defined as P1 and Pn, and then each person tracker will produce a bounding box tracking called TR, which is the tracking result of this person tracker CMT. During the identification process, we need to assign a specific person P, tracker P, to the specific bounding box B, and meanwhile in the tracking process, we need to keep associating the result of CMT with the result of POM. That's the main idea, and update the appearance model of person tracker P. So in the identification process, we assign a person tracker. In this case, this is a raw detection of the POM, and then we give a specific identity for this kind of person during this specific frame. This is person 1 with the bounding box green, and then this is, if in the case of 3 person, this is already blue, green, and we give a unique identity as red in this case. And then how to determine the center ground points? We use this equation, very simple equation, just to find this center ground points of the POM. This is the white is detected bounding box of the POM, and then the green one is the predicted tracking result for CMT, and we get the center ground point. And then we calculate the distance between them. Let's say the distance is less than a specific parameter, then we can associate these two. In this case, it's only single target. But how about if we tracking more than 2? We use the same method, but very expanded using a global nearest neighbor. So we just calculate the minimum distance between them. So this one, we calculate the minimum distance, this one and this one. So we can get the idea that it will always associate to the minimum distance, whether this is 2%. And then for the 3%, we just added some more D1, D2, D3 to associate these all 3 bounding boxes to get the correct association between the detection and the tracking. And how to handle the occlusion? We do, first of all, we only do the tracking in here and then distribute the tracking to other camera view. But what if this camera is occluded? So we switch the tracking process to another camera which is not occluded here, and then distribute this result to another camera view. This is the idea. How to do that? Is based on the same idea again, but now we calculate the center ground points of each bounding box, B1 and B2. We calculate the Euclidean distance of the center ground points of B1 and B2, and then if it's less than the parameter, specified parameter, then it will be said that this is occluded. Same as for the rest camera. Experiment result, we do some experiment on 2 datasets, log4P and log6P, which is all the lab is the same room, but different people coming in, and then we use the standard matrix of MOTP and OTA to evaluate here. The given equation is like this. So the result is here. As we could see that actually this result is based on 3% tracking result. For each data set, we only track up to 3%. At the first video, we got 93% because there is some false negative here. We lost the target tracking because we didn't employ the occlusion handling, but the next one is we employ. The second video is more easier. Without the occlusion handling, also we can get 100%. And the computing time necessary for each video is defined here, 1, 2, and 3%. And then this one is the result of the tracking result. So the first row, it's using the occlusion handling. The second row is without the occlusion handling. At some point, the without occlusion handling will lose the track of this person, the green color. I would like to notice later. nearby the end of the video where there is a, how to say, significant occlusion, there will be a miss, how to say, a miss tracking. So whatever, if there is some occlusion here, they will be moved the tracking to here. As we could see, there is the key point is moved here and go back again if there is no occlusion in this specific camera view. And around frame 900, there will be some significant occlusion that cannot be solved if we didn't switch the tracking view. So they will lose, especially in this case. So the green is loose. They cannot track because in this case, in the first row, we do this camera switching. We do the tracking in here, not like this one without the switching. So due to time constraint, I skip the second video result. We skip to the conclusion. We simplified the multi-camera tracking problem into single camera tracking by using the geometrical mapping advantage of PON and then employ the global nearest neighbor association to solve the tracking problem and then propose a camera view switching mechanism to overcome occlusion problem. And in the future work, rather than focusing on the tracking approach, which is restricted to the camera view, we just directly process the detected bonding blocks of POM and finding the association between them. And then this next one is to improve the ground discretization result in order to minimize the projection error. After that, we could test on more data set in the future and with more people. That's all.
Can you explain again how you perform, from the image you take from the different cameras, so how you perform, how do you call it, yes, how do you map onto the ground, how do you call it?
Ground plane discretization?
Yes. And
this one,
right? Yes. So what do you use exactly as techniques?
DLT.
So this is what you explain at the end, which is direct linear. This is just linear transformation, right?
Yes.
What is SOM?
SOM is the background subtraction.
Sorry. What does that stand for?
SOM. SOM is how to say? SOM. Mapping, something like mapping. I forget the name. I forget this short. What is the? Yes, I'm sorry. I forget the name. Yes, I am. Self-organizing map. Sorry, self-organizing map. Self-organizing map.
What I
Yes.
usually understand.
Yes, I'm sorry.
Okay. So maybe it's because your presentation is, from my point of view, quite clear, but I don't see really very difficult problems except conclusion.
Yes.
Right?
Yes.
So can you solve conclusion by just switching from one camera to another camera?
Yes.
So I would expect that when you shift from one camera to another camera, there is a small load in computation. At that time,
Yes.
yes, so you have to take a decision and then you have to go to the other camera.
Yes. At first we.
Can you give
Yes.
us some comments on how, well, more precisely, so how would you make a decision? Well, no, you make a decision just
So-
to another camera. Oh, yes, so by the way, another camera is, you don't choose the camera, you just go to the next camera.
Yes.
Yes, that's all, there is no decision.
No decision.
Yes.
If this is camera 1 is included, so we just simply move to the next camera.
Okay.
But this one actually, what we also face problem. That's why we call it in the future work. We doesn't want to do this anymore. Rather than restricted our approach using camera view like this. Camera 1 is included, move to camera 2 is included, camera 3 It is because in this case, it's easy if only two bounding box. We only simply calculate the distance between this. But what if the person is more than 2, 3, 4? How the decision would be? It will be more complicated. In this case, this kind of simple decision algorithm, it's not work as we expected in this case. So in our current proposed method, maybe it only works for less than 5 people. 4 maybe makes sense, but other than 4, it cannot be used as this simple conclusion method.
I will have a last question. Usually we say that human beings,
yes,
not all animals,
yes,
have a special view.
Yes.
It's because in fact we have 2 cameras and
yes,
they are near to one another.
yes.
And so if you would put your 2 cameras very near to
by
one another,
yes,
right? What would be the results that you would expect? Would you still have the occlusion problem, and what would you propose in order to solve it? So my question is, how would you simulate human vision?
Yes, if that's the case, we cannot solve it. Because this idea, we need to stress on that every camera view put it in a very different angle view. So in this case, something like the first one, we give a sample setup, typical setup here. If this camera is put a really same view angle, then they will always see a view that is occluded, unless they provide this camera view, look here, and look here, a very different angle view, then it makes sense, because our main assumption here is at least all of the camera we use, at least one camera could have a clear view, then we can always solve the occlusion problem. That's the main idea of our approach.
Okay, thank you.
What kind of application
Okay, so in this case, we use this kind of application for a specific room, which is an indoor specific room, which is required high level of security, where there is a person coming in, and not so many persons can come in the same time, but we can always track that person and then identify that there's a different person. If we let's say we already store this specific person identity 1, and then whenever they come, we can count as 1 is coming to the room, and then the specific person 2 is coming to the room. So we can always count and also track the trajectories. In this inside room, what are the people doing? This one example for surveillance. And the next example is for something like retailing behavior. We analyze the behavior of the customer. Let's say it is put inside a shop and there is a lot of goods to sell. So we can know that this person consumed time a lot in this specific location of goods. Maybe this goods is very, interested them. So based on this behavior analysis, with tracking, we can specify a person identity here. So we can differentiate. So we can know that this specific person, in this case, interested in this kind of goods. So it can be used for behavior analysis.
The layout or something, it is changing something affect your
Layout. Yes. Each layout needs a different, because we assume that yes, we assume that we got this specific 3x3 homography matrix for each camera. So for each different layout, they will produce different homography matrix depending on the camera. So to implement this correctly in each dataset, we need to get this 3x3 homography matrix.
So you need to update it may change.
Yes, correct. The correspondence might change depending on the different dataset. Any other questions?